Lesson 34, graphing sine and cosine functions. All right, so as we get graphing these different functions, we're going to be coming across things like, period and amplitude and median and these things. Now, this is a great reference for you guys to use, especially when you're studying, to have this just on the front page here. I'm going to just get into some graphing and then kind of explain where these things come from. And to show you how we're going to graph this, I'm actually going to use a little gizmo thing here. So I have a link for this on the website there, so you guys can play around with it too. But this is called Trig Tour because we're actually just going to show what these graphs are looking like. So this should look familiar, right? This really is a unit circle that we have going on. And I can even put my special angles on there, right? So if you see, if I bring it up to there on that first angle, then if I'm in degrees, then my angle would be 30 degrees right there, right? That would be 30, 45, 60, and 90, right? So we'll just kind of stay in this first quadrant for the time being. Now, I'm set to cosine, so it's saying right here, right, this point right there, hang on one sec, right here would be root 3 over 2, right? That's like the cos value, right? That's my x value or my cosine x value, or cosine theta, doesn't matter. So it's set to cos right now, but I can set it to sine as well, right? So sine, it's saying it's a half. And that should make sense to you too, right? So that we know this from the unit circle, right? That point there is root 3 over 2 and then a half, and that would be my sine x value, okay? So that's the idea that's happening right now. Do you also see that if I start off with a let's do sine graph first, right? They're showing us the length of the opposite side for our sine graph, right? So if I move this thing, it starts at 0, okay? So our sine value, when it's at 0, or when the angle is 0, is also 0, right? Like my height up and down is nothing at that point. And then look what happens when I move it up. Now it's at a half, and then you're probably used to this. The next one I move up is going to be root 2 over 2, and then the next one would be root 3 over 2. That'd be the length there, and then all the way up to 1, okay? So why that's going to be important, let's actually turn the graph on now and see what this looks like. So here is a sine theta graph. So when I'm looking at this graph, theta, or I was calling it x up here, is my x-axis, right? So there's theta. So as the angle increases, so as the angle goes up this way, then sine theta is going to be, well, it's these values, right? This is my values for sine as this thing is going up and down. So right now we're at the point 0 because we're at 0 right there, okay? But watch when we move it up. Do you see that the length, right now it's a half right there? Now I'm at a half on my y-axis. Okay, so a sine graph, a sine theta graph, is really telling you what the value of y is at any given point on the unit circle. So let's keep going around. So if I go up again, now I'm at root 2 over 2, would be about there. And then the next one up would be at root 3 over 2. And then when I'm right at the top here, now I'm at 1, right? The peak of this graph is going to happen at 1, and it's not going to go above that point 1 right there on our axis, okay? And as we keep going around, now we're going to the back side. So now I'm at root 3 over 2, root 2 over 2, a half, and then I'm back to 0, right? I have no height anymore for my y. And then I just start going into the negatives. So now I'm at negative a half, negative root 2 over 2, negative root 3 over 2, and now I'm at negative 1. So now I'm totally flipped upside down at that point, okay? And then we'll go around again until we get back to the start. All right, so that's pretty much it, right? That is going to be our sine graph, and that's the idea. So I just want to really make sure you guys get that idea. Now let's turn it to radians as well, and you'll just kind of see that if we're in radians and I go up here, then it's saying the angle would be pi over 6 at that point, and then all the way around, okay? So notice where these things happen, right? That we're going to have a peak at pi over 2. And that makes sense, right? That's when it's all y, right? The y is at 1 at that point. And then we're going to be back down to 0 at pi, right? So this would be the point pi. Oh, I could probably put that label on. There you go. So you can see pi there now. And then moving around, I'm at a peak again at 3 pi over 2, right? That's halfway between pi and 2 pi. And then it goes back. All right. So I think I've explained that one enough. Now let's change it over to our cos graph. Okay, so cos graph, here, let's even just change back and forth. Do you see how those are like the same graph? They just start in a different place. But doesn't that make sense? Because now look at what I'm measuring, right? The blue arrow is the length of my x, right? That's this. We're talking about my x values at any given point here. Okay, so to begin with, when the angle is 0, well, that means it's all x, right? It's a length of 1 at that point. So that's why for a cos graph, we're going to be starting at the top. We're going to be starting at 1. And then as we move around, now my length is going to be root 3 over 2, root 2 over 2, a half. And then when I'm at pi over 2, now I'm at 0, right? There is no x happening here at all. There's no cos x or cos theta happening there at all. And then you just get the same idea as you go around. Okay, so now that we've gone through that, let's go back to our notes. Okay, so then we're just going to have certain aspects of our graph that we're going to have to recognize here. So again, I'll draw some examples here below, and we'll go through what the period is, the amplitude, and the median. Okay, so let's sketch our sine function, just really using what we did before. I won't do all the points, but I'll kind of do enough here, and please do it with me. Okay, so what I'm going to do is make my scale along the axis. So I'm going to make every 4 boxes, that'd be my 1. Okay, so that'll be like 1 up there. And then -1 will be down here on my y-axis. Okay, and then for my x values, and remember my x values here really are my theta, right? They're my angle is what's going across the x here. I'm going to make, every 3 boxes will be 60 degrees. Okay, so 60 degrees, and that'd be 120, and that would be 180, and then 240, and then 300, and then 360, right? So all the way around the circle. So yeah, we're doing it in degrees right now, but we could do it in radians as well, and we'll do that for the cosine function on the bottom one. Okay, so if we were sketching this thing, then just thinking of our unit circle, right? So if this is our unit circle, and here, actually I'm going to make it like this, then if we think about the value of our y, right? That's what we're doing. We're doing a sine x function. We're thinking about the value of our y at that point, right? So at that point on our unit circle at 0 degrees, then that would be the point 1, 0. Our value for y, or our value for sine, is 0, right? So we're starting at 0. Okay? And then I'm just going to do the main points here, and we'll kind of fill it in. At 90 degrees, right, at that point, now I'm going to be at the point 0, 1, right? And that's at 90 degrees. So if I go, partway between 60 and 120 here, or in the middle of them, then I'm going to be all the way up at 1. Okay? And then when I'm over here, right, now I'm at the point -1, 0. So my y is back at 0. So at 180 degrees, I'm back at 0. And you can probably see the pattern happening here. I'll just do one more. So at this point, now we're at 0, -1, right? So our y value is -1. So at 270, so between these ones, we're going to be at -1. And then all the way around again, we'd be back at 360. So there we go. There is our, and just do your best to make a curve, right? They should be, yeah, like curve, something like that, right? Okay, so now that we have that, we want to figure out, you know, just what are the x-intercepts, y-intercepts, amplitude, period, and median. So the x-intercepts, where are they happening? Okay, well, they are happening at 0 degrees, 180 degrees, and 360 degrees. And technically, we could write out a little general equation for that too, because this thing would have also went this way, couldn't it? We could have had negative angles going that way. So the actual, well, maybe a little farther down, but whatever, you get the idea. The actual x-intercepts and like the general solution there, we could have said that they'd be equal to, so the x-intercepts could be equal to 180 degrees times n, where n is a member of the integers, right? So that would account for all of it as well. So you could write it in a general form like that too, right? Because it's always going to hit those 180 steps, right? In the positive and in the negative as well. So the integer part of this allows for negative numbers, right? So that would allow for me to be into the negative. Okay, so our y-intercept on this one is at 0, okay? So that's always going to be the case. Well, it won't always be the case, but for just a standard sine graph, it'll start at 0. We're going to be doing transformations and everything next lesson, so that won't always be the case. But all right, so the amplitude. So what do we mean by the amplitude? So the amplitude of a wave function is going to be the distance from the midline, so from like where this thing is going around. Okay, so if I maybe use a different color here. So this would be my midline right here, right at the line y is equal to 0, or the x-axis in this case, right? So your amplitude is going to be the distance from that midline up to the peak, right? And it's actually down to the peak there as well, right? So it's actually the absolute value, right? So you could think about it as being like the positive version of whatever that is, right? But it is just the distance, like how big it is from the midline up to the peak. So the amplitude in this one would just be 1. Now, one thing I just want you to notice is that up here we had a formula for amplitude, didn't we? We had A is equal to max minus min divided by 2. Okay, well, does that make sense? So if I drew out this thing, right, and we like went up here and then went down there again. So what this means is our max would be at the point 1, right? If I'm just thinking about my y values here, right? Comes up to 1 and then goes down to -1, right, at that point. Then yeah, this would be A is equal to 1 minus -1 divided by 2, right? So that's going to be 2 over 2, so that's 1, right? And what that found was this. What this formula is really doing is just finding, so max minus min, that just found your total height of your wave, right? The whole thing. And then dividing it by 2 just gave us half of that wave, right? So just from there to there. Okay, so that's all that formula is. It's just a way of figuring out what the height of half of our wave would be, right? Okay, so yeah, so that's our amplitude is 1, but yeah, we could really just see that from the graph too, couldn't we? All right, the period. Now, the period of the graph is going to be how long does it take to do, well, not how long, but for 360 degrees, right? So in this case, that's going to be, the period of the graph would be from where it started, right? So from 0, and then to, let's do a different color here. So it's going to be like from where it started, here, even different color than that. Ah, good enough. To, well, do you see how like one cycle, well, halfway would get you to there, and then the full cycle would get you to 360 degrees, right? That would be all the way around the circle. That would be starting here and going all the way around, right? So that would be the period. Okay, so this is the same idea if any of you guys have taken physics. The word period is how long to do one circle in physics. Okay, so the same idea here. So the period would be 360 degrees. Or if we were dealing in radians, it would be 2 pi, right? And again, in the next lesson, we're going to this will change, and we'll talk about how to find that as well. So the period is going to be sorry, not 2 pi. We're talking radians or degrees, so it'd be 360 degrees. Okay. Now the median, or it's called the midline sometimes. The midline or the median is going to be the line y is equal to 0, right? That's just going to be along the x-axis. And that's just like where it's, you know, going up and down around, right? So that's the middle line or the median. All right, the maximum. So your maximum is going to be when y is equal to 1. Your minimum is going to be when y is equal to -1. Your domain, all right, your domain, this thing actually would go on and on forever either way, right? So this would be x is a member of the real numbers, and your range would be y is greater than or equal to -1 and less than or equal to 1, okay? Or it'd be -1, 1, written either way. All right, so now we'll do the cosine graph, and this time we'll do it with radians instead. So for this one, all right, so on this one, again, we're going to go up every 4, and that'll be my 1, and then down 4, and that'll be my -1 on the y-axis. Okay. Here, you know what? Instead of calling it the y-axis too, why don't we call it cosine theta or cosine x axis, because that's really what it is, right? Okay, and then going this way, or going along our x now, so this will be like our x's or our coses, or our thetas, I mean, sorry, be the same thing on this axis. I'm going to make every 4 pi over 2, just to change it up on you. So pi over 2, which would make another 4 would be my pi, and then another 4 would be 3 pi over 2, or like 270 degrees, and then right there would be 2 pi, so all the way around. Okay, so now if we think about this one for cosine, right, so if that's our graph, then so cos was this, right, like that's our length here. So at that point right there, at our beginning point, would be the point 1, 0. So this time, we're starting at 1, right? We're starting up here. So a cos graph will always start, if it was just cos, up at 1. And then up at the top, it would be at 0, 1. So it's at 0 at pi over 2. And then I think you get the pattern, right? So I'll just kind of carry on from there. So then it's back up here, and then up to here again. All right, so then our graph starts at the top, comes down, the bottom, and then up again. So looking something like that, right? And it would continue on, right? So this pattern would keep going, wouldn't it, on both sides? You could end up with negative angles going down, and you could go past 2 pi as well. So there's your graph there, right? All right, so x-intercepts on this one. So our x-intercepts are going to be at, so it's going to be at, like, you know, pi over 2, 3 pi over 2, and following with that pattern, right? It would also be at negative pi over 2 over here, right? So it looks like we're doing pi over 2s all the way up. So why don't we do this? Why don't we say that this is pi over 2 times n, or pi, or yeah, either way, pi n over 2 or whatever, where n is a member of the integers. And yeah, that should handle a day. Remember that integers could be negative, right? So that handles them all over here as well. So then our y-intercept is going to be when y is equal to 1. Our amplitude is still 1, right? It's still going to be 1, like up and down there, and then the same here. It's going to have a value of 1 for now. So 1. Our period, well, our period, so in the last one, maybe I should explain a little bit more about this too, right? We said it was 360, so that was from here to here. But actually, it doesn't matter where you take it. So what it is, do you see how the pattern at the beginning on our sine graph was going up here, and then it would start going up again here? So we can actually look at any place on the graph. So if this went up again here, right, to there, it would also be 360 degrees from there to there, right? You can actually pick any point on the graph, right? It'd be the same if it was, you know, from here to here if you really want to. That would also be 360 degrees from there to there, right? So it doesn't actually matter where you look at it. So we'll do the same thing here. Let's look at, we'll go from peak to peak. So from here to here is going to be 2 pi. right, from there to there. So that's our period, is going to be 2 pi. Our median is still the middle. That's still at the line y is equal to 0, is what it's going up and down around. The maximum is still going to be still going to be 1. Y is equal to 1. The minimum is going to be y is equal to -1. The domain is x, or theta, is a member of the real numbers. And then the range would be y is greater than or equal to -1, less than or equal to 1. All right, so now this one says, how are the graphs of y is equal to sine x and cos x similar? How are they different? What changes can be made to turn sine x into cos x? All right, so if we look at, well, here, you know what? Let's look at this. It might be a little easier. So if we can see cos x and sine x, those graphs, right? Do you see how, like, if I have sine x, it starts at 0, and then cos x starts at 1? Well, just kind of imagine that we shifted. Imagine if we shifted the sine x, right, here, just over, right? We shifted that back over to here. Well, that would be exactly the graph of cos x, wouldn't it? If we shifted it over just like that. So this is what's called a phase shift. And actually, we could shift it over from there to there. Or we could shift it all the way from here over to there, and that'd be fine. We could shift it from here over to there. And it actually doesn't matter, right? So we can turn a sine graph into a cosine graph just by shifting it back and forth from left to right. Okay, so you guys should be a little familiar with this. This is going to be a horizontal translation, isn't it, from stuff we've been doing before. But when we're talking about sinusoidal functions, this is going to be called a phase shift. All right. Now, getting into a bit more of these transformations, what we're dealing with here, right, before we get going, just so this looks a little bit more familiar, these will be on your formula sheet. I'll show you where. So you will see on your formula sheet here these two formulas hanging out at the bottom. Now, these formulas should look a little bit familiar, don't they? Don't they look exactly like our, well, not exactly, very similar to our general formula? And that's because they are, right? The function in this case, right, the f, is really just going to be either a sine or a cosine. So they're on here anyway, just so that they can remind you, but they're the same thing. But now, just in this case, it was b and, you know, h and k. What's going to change here is these are just c and d, but they behave the same way. They are really the same. They just kind of call them different numbers, typically with sinusoidal functions. Okay, so all right, so now this one says state the amplitude of each trigonometric function. So we have y is equal to 1/4 sine theta. All right, so if we remember this, like when we have a number out front of our function from before, right? That was really just our a value, wasn't it? And this will still be the a value, but this a value is going to be our amplitude. Okay, so then the amplitude of our function is just going to be a is equal to 1/4, right? And let's just kind of think about that for a second, what that meant. So if we took our sine function, just our basic sine function, so back up, right? So that means that we're multiplying, so here's our sine, right? Every one of these values, right? So like, let's say this value here, it's being multiplied by 1/4. So the y values are being multiplied by 1/4. So our new function, that value right there, would be squashed down there, wouldn't it? So our peak, that was, like our amplitude was from here to here. Well, now on the new function, when I multiply it by 1/4, it's only going to be here. So our amplitude would now just be 1/4 if we multiply it by that. So then this graph would do something like this. It would go like up here, stop down there. It would still go through there, and then it would go down to -1/4, and then back up again. So that's what would actually happen to that graph, right? So that's the idea there. All right, so now looking at this one, I can just ignore the 1/2 for this question because it just wants the amplitude. So the amplitude of this one is going to be, well, -3. Okay, so that, let's see if that makes sense. So A is going to be our -3. Okay, so what's really happening here? Like this is going to, we're going to have a vertical stretch of -3, right? If we were using the terms that we've done in the other lessons there, right? So what that means is that, let's say if I took this point right here, right? Like where we started. Okay, so that is at the point 0, 1, right? So when we have a vertical stretch, that applies to the y value. So that point now is going to be multiplied by 3. So, you know, it'd be actually be like up here now. But technically, since it's multiplied by -3, it's actually going to be down here, isn't it? It's going to be way down here. Maybe not that far, right? At -3. So that would be at the point 0, -3 now. So the whole thing would be flipped, right? So we multiply it by 3 and also multiply by negative. So this would also be a reflection in the x-axis, wouldn't it? Which you guys should be used to those, right? When we reflect over the x-axis, that would be the number out front. So anyway, our actual amplitude, though, remember, our amplitude is like the absolute value of where we're at. So this is going to be just an a value of 3. Okay, so we just wouldn't write the negative on there as well. Okay, so for this one, it says state the period of each trigonometric function in degrees and in radians, right? And this time they've actually given us the b value, right? So if this is using our general equation there, right? This would be our b. Let's look back up at the beginning here, right? So this is on your formula sheet. Sorry, I lied. This is not on your formula sheet. This will be up to you to memorize. Here's our formula, right? So this is period is equal to 2 pi over b, or if you're dealing with degrees, it'd be period is equal to 360 degrees over b. Okay, so again, right? So if we were dealing with, here, let's write out the equation. So this one's cos, so it's y is equal to a cos, and then it's b times x minus c, and then plus d, right? So we're dealing with that b value right now, right? So you guys probably remember that this b value, if we were looking at the actual graph, right? This is your horizontal stretch, and it was always doing the opposite, wasn't it? So if this was like, you know, a value of 3 for my b, remember how it actually happened on the graph was actually a factor of 1 over 3. Okay, so that's the same idea here. So our b value is stretching the graph by a factor of 1 over b, right? That's all they're saying there. Okay, now, to give you an idea why this equation works, I just want to rearrange this a little bit. Okay, let's actually just switch the b value, right? So let's say b, and I'll just drop the absolute value bars for a second, is equal to, and then that's 360 degrees divided by p. Okay, so that's b over 1, right? If I rearrange that or flipped it, this is the same thing as saying 1 over b, right, is equal to p over 360 degrees, right? So let's say that your period was 720 degrees, right? That's how long it took for, so 720 degrees. Here, I'll write another one. So p, okay. So looking at this, your 1 over b value is how much the thing is stretching, right? So this is saying it's stretching by a factor of whatever the period is divided by 360 degrees, because 360 degrees is where cosine, that's its normal period, right? So it's really saying by what factor, like how many times bigger is p than 360. So as an example, what if I put in like 720 degrees over 360 degrees, right? Well, that would be a stretch factor of 2, right? So that would mean that every point on the graph would be stretching by twice as much. So if you had this graph like down here, all of these points would be being stretched twice as far to the right. So the whole thing would get like stretched sideways. Now if I put a point like, you know, so I said 1 over b is equal to, what if this is 180, right? 180 degrees over 360. Well, that'd be the same thing as a half. So in that case, the actual stretch factor that would be happening would be pulling it in, right? The whole thing would be like an accordion squashing in, right? So to show what I mean by this, let's actually look at this graph on Desmos here. So I know you guys can't really see like the left side here, but there's a y right there, and there's an a is equal to 1 right there. So the way that this graph works is this is y is equal to cosine, and then there's my, I should have made that b, it would have made more sense. Okay, so that's my b value right there, is which I called a, times x, right? And right now, a is just equal to 1. So this graph right now really is the graph of y is equal to cosine x, right? But I can change this value of a now, right? So I can change that value to 2. Right, so if I put 2 in there, then do you see what happened? The whole thing squashed inward, and it squashed inward by a factor of a half, right? So it multiplied everything by a half there, didn't it? So if my a value is 2, the whole thing squishes in. Okay, so if I made that, 10, then it should squish in quite a lot more. There, and I get that accordion idea, right? And then the other way, it happens the other way as well. So if I made this like so if this is 1 to begin with, okay, I could also make that a half, and we'll see what happens. So if that's 1 over 2, then you see how the whole thing now is stretching out, right? So that's what's happening there. Hopefully that makes sense. So, okay. I was showing you guys that just so you understood the y part of that, but now we have that nifty little formula. If it's saying what's the period of each trigonometric function in degrees and radians, well then if I know my b value is 2, then I have my equation of b, the absolute value of b, is equal to, so it wants degrees and radians, so I'll do it in degrees first. So now I know it's going to be 360 divided by the period. So then the period would be equal to 360 divided by 2, right? My b value is 2. Oh, sorry, I'll rearrange that. 360 divided by b first, and then put it in. So that would be 360 divided by 2. Okay, so that would be a period of 180 degrees. And doesn't that make sense, right? If this is a 2 value in here, the actual stretch would be 1 over 2, so it'd be a half. So when it was 360, now it's 180, right? So it's everything has been like squished inward in that x direction, right? That's our horizontal stretch. Okay, so same thing with radians. So if we were going to do that one with radians, that would be everything would be the same, but it would be p is equal to 2 pi over b. So that would be 2 pi over 2. So your 2's would cancel, so that'd be the same thing as pi radians. All right. Next one here. I'll just do maybe just in radians for the time's sake. We only have to, if we're worried about the period, well, that's only the ones that are that's only the horizontal stretch that's going to be affected there, right? So I don't really care what the amplitude is, right? The amplitude can be as high as it wants. That's not going to affect how squished it is in the x-axis. Okay, so I'm only looking here. So this would be period is equal to 2 pi over b, and my b value is 1.5. So now you can put it all into your calculator and you get a number in radians, but I'd like to leave the pi if I can here. So you know what I'm going to do? I'm actually going to rewrite this 1.5 as p is equal to 2 pi over and then 3 over 2. And then dividing by a fraction is the same thing as multiplying by the reciprocal. So that'd be 2 pi times 2 over 3. So this would be the same thing as 4 pi over 3. All right, moving on down. So now it says find the period and amplitude of each trigonometric function. Okay, so they've just given us the graph this time. We just have to know where to find it. All right, so in this case, we can see for the amplitude that the amplitude would be from there to there or from there to there, right? Just the absolute value of that. And this one is symmetric across the x-axis, so it really just would be our y value at that point, wouldn't it? So a would be equal to 0.5. Again, we could also find that though using our equation that isn't on your formula sheet, but really is just figuring out what half of this graph is. And that would be if we went A is equal to the max minus the min, or yeah, so minus the min, and then divided by 2, right? So A is equal to 0.5 minus negative 0.5 divided by 2, and that 2 would give you 0.5. All right, now the period. So the period in this one, well, looking at the graph here, I can see from here, if I actually do cross through 0, and then if I go to this point, this is 4.71. Can you see that that would be half of my period, right? This is like halfway there, and then it's to here would get me all the way there. That would be one full cycle, would be from here, and then I start going back up again here, right? So from that point to that point. So I just really need to go this 4.71 times 2. So the period would be equal to 4.71 times 2, okay, which is equal to 9.42. All right, looking at the other one, we've got our A value is 2, our amplitude, and then our period would just be, well, you can see from here, it starts here, right? And then halfway through, I'm at 60, because full period would be from there to there, right? It would be from that point to that point. So halfway through, I'm at 60. So in this case, our period is just going to be 60 times 2. So 120. And this was in degrees, looks like. Okay. Okay, last graph here. So now we've got the tangent function. So again, what I'm going to do, let's go to that trig explorer. Okay, so if we're back here, what we're going to do, I'll turn back on my special angles and my labels. And then this time we're going to switch over to the tan graph. I don't want to give it away yet. Okay, so if I move up here, right, now they're showing the blue and the y, or and the green, because that's my x and y, right? And remember what tan is. Tan is my y over my x. It's my opposite over my adjacent, right? So at that point right there, it's root 3 over 2. If you like simplified those, right? If I went 1/2 divided by root 3 over 2, and then rationalize the denominator, I end up getting root 3 over 3. Okay, so that's what that would be equal to. And then as you go up, then we're at 45 degrees there now, right? So this would end up being y over x would be equal to 1, right, at that point. And then as you go up, we're getting bigger and bigger, and then at that point, now tan theta says that y over x is equal to infinity, like plus or minus infinity, right? Let's see why that works. I'm just going to turn my special angles off and look at this now, right? So I think I should be able to just kind of, yeah. So we can see, looking at what we did before there, as we're going up, right, then our green arrow divided by our blue arrow there, right, because that's what tan is. It's the green divided by the blue. Well, as the green gets longer and longer, do you see how the blue gets shorter and shorter? Up until the point, let's say right here, when we're getting right up next to it, the blue arrow is getting tiny, tiny, tiny. Okay, and when you have a number, even like 1 in this case, right, if I'm getting there 0.9 for my y value, like getting very close to 1, well, my x value is getting like very, very small. So like if I go 0.9 divided by some very, very, very small number, I end up getting a very, very large number, right? That's why this one's like going off the charts. It keeps going up and up and up. Okay, so if I keep going closer and closer, notice what happens, if I can do this, that it goes, well, it starts going toward infinity, right? This thing goes off the charts upward. Okay, this looks like the making of an asymptote, right? And that is, so on the graph of tan theta, we get this kind of weird pattern like we have below here, right? Where we're going to have an asymptote at 90 degrees, right? Because that's where we've got our y value of 1 divided by an x value of 0, right? So we get an asymptote there. And then as we come around the other side, think about this too. So now what we have this green arrow divided by the blue arrow, but now the blue arrow is negative, right? Our x's are negative on this side. So now it starts down low here. It starts down on the bottom part of the graph because now we're into negative territory. And then we work our way around and then back up to 0. And that 0 makes sense too, doesn't it? Because at this point, we have a y value of 0 and an x value of 1. Well, that's fine. If I have 0 divided by 1, that's just 0. Okay, so that's why we're on the graph and we're all good. But then as we keep going around, we run into that same issue again, right? And now this time, I'm into the positives again up here, right? And why am I in the positives? Because now I have a negative green arrow, right, like negative y, divided by a negative x. So then my tan would come out positive over here. And then as we go around, we end up in that negative territory again, because now I have a positive x and a negative y. And then we'll go back up to 0. Okay, and then that pattern continues. It just goes around and around and around. And you would get the same thing happening with radians as well, right? So it'd be the same idea as you're going up and around, okay? So now that we went through that, I'm gonna make a graph of this, just make my own graph here. And I'm gonna go up by, okay, let's say 1 is every 4. So that'll be 1 and that'll be 2, -1, -2, okay, and 0, obviously there. And then we'll go up every 3 will be 60. So we'll go 60, 120, 180, 240, 300, and then 360. All right. So then remember where our vertical asymptotes were at, right? They were at 90 degrees. So we would have a vertical asymptote here. Oh, I'm writing with the wrong kind of pen. One sec. I'll keep doing it this way now that I've started. So we'd have a vertical asymptote at 90 degrees, right? For the reasons that we just went through, right? So we have a vertical asymptote at 90 degrees. Okay. We also knew that we had another one at 270. Okay, so we'd have another one happening here. So 270 degrees, so vertical asymptote at that. Okay, so now we'll just kind of fill it in. You know, I'm not going to get too into the weeds here. This thing would start, it was at 0, right? And then it went up toward infinity. And then it picked up down here again, didn't it? And it crossed through 180, right? So that'll be a good point to draw first. So it starts down here, does like a bit of a squiggle coming up. And then on the other side here, it starts back down here again, and then it passes through 360. So it'd be down here, and then it would start going back up again. So there you go. There is our standard tangent graph, right? And this thing too, this would come down here, wouldn't it? Into the negatives. It would do the same thing on that side. Okay. Okay, so I made this with a pen that actually just follows my screen, so I'm gonna have to delete this. But yeah, hopefully you guys get the idea, and hopefully you make the same graph there. So I'm just gonna erase that now. So clear that, and then for 30-1, you guys are responsible for just understanding just the basic ideas, everything I just kind of took you through there with the graph of how the tan function works, right? We're not going to be doing any translations or anything else with tan functions, but you will need to know like the period of it, the equation of the asymptotes, and those things, right? So let's just go through this and make sure you understand this, and then we should be good. So the x-intercepts of a tan function would be at, well, they were at 0, and they were at 180, and they were at 360, right? They were at those points. So we could say they were at 180 degrees n, where n is a member of the integers, right? So that's a good question for you to be asked, right? So they'll say, where are the x-intercepts on a tan function? You need to know that that's where they would be, okay? The y-intercept, so where does the y-intercept happen? So the y-intercept happens at y is equal to 0, right? That's where we start. We started at that middle, or at the origin there. The equation of the asymptotes, again, this is a great question for you to be asked, right? So this would be at 90 degrees. this would be at 270 degrees, right? And so on. So going up by 90 degrees or 180 degrees after you get to 90. So a good way to write this in a general form would be, well, I can't really go 90 degrees times n this time, can I? Because that would be in steps of 90 degrees, right? So that would be 90, 180, 270, but I don't want the 180, right? So what we're gonna have to do is start with 90. We'll say, okay, 90 degrees, and then how much I want to turn from there, right? So I'm gonna start at 90 and say then plus 180 degrees from there. And now I'm going to multiply that by n. Okay, so that could be 1, 2, 3, or 0, or -1, -2, right? So those are the numbers for n I could put in, where n is a member of the integers, right? And then that should cover all of my different, equations of my asymptotes, right? So it could be asked this way. I just want to make sure you guys understand that if it was multiple choice, then you'd have to know this, right? And then it could be written in radians as well, okay? So the period of this graph, okay, so let's think about the period of that graph there, since I erased it up top. Let's look at this one. So how long does it take to repeat the pattern? Well, notice that started, well, if we started right at the beginning here, there, right? So it's going up from here, right, at that point, and then it's going up from here at that point, right? So it's repeating the pattern again from there. Or you could go from asymptote to asymptote, but the period's actually going to be half as much as it is on a typical graph, isn't it? So it repeats every pi radians or 180 degrees. Okay, so our period would be, so P would be equal to 180 degrees or pi, every pi. All right, so the median. So this thing is still happening around the line y is equal to 0. So even though it goes to infinity, like positive infinity and negative infinity, it's still all happening around that x-axis, right? So it's still going to be 0. Your domain of this one, right? So your domain, this is another great question that can be asked, like what's the domain of a tangent function? You could say that, written out formally, x cannot equal, oh, come on, pen, cannot equal 90 degrees plus 180 degrees n, where n is a member of the integers. Okay, so pretty much just like the equation of our asymptotes, isn't it? Because those are the ones that we're not allowed to use, right? So yeah, this is formally the way that you would see it though, right? All right, and then the range would be, well, the range can be anything, can't it? Doesn't it go like positive infinity and negative infinity at times? So that's going to be y is a member of the real numbers. All right, so like I said, the tangent ratio is more like the theory behind what it is and how it works, and we're not going to be doing much more other than that with the tangent ratio.